Okay, in this video we're going to be looking at various applications of derivatives and how we can apply them in different real-world contexts. So the first one is talks about freefall. You're dropping a ball from the top of a building. The height is modeled by the function s equals 144 minus 16t squared meters after t seconds. How long does it take the ball to reach the ground? And then the second question, what is the ball's velocity at the moment of impact? Well, when it reaches the ground, all right, so that's important to know. When it reaches the ground, that means s equals 0. So what we're first going to do, all right, is we're going to set our s function, which I'll rewrite again. We're going to set that equal to 0, because that means that the ball's on the ground, all right? The ball's on the ground at that point. All right, we solve that. We get something like 144 equals 16t squared. You can divide both sides by 16. Okay, simple square root property there. All right, and you get something like, what is it? Okay, 144 over 16 actually doesn't go in evenly, does it? Or it does. It's 9. Okay, it's 9. So 9 equals t squared, and we take the square root of that. T equals plus and minus 3. So it wouldn't make sense for us to have negative 3 seconds, for example. So actually the only answer is 3 seconds. So how long does it take to reach the ground? 3 seconds. Okay, so that's the first question. All right. The second question is, what is the ball's velocity at the moment of impact? Well, it impacts at 3 seconds, right? So in order to find the velocity, we have to find the first derivative, s prime, which is the velocity function. And we're going to get derivative of 144 is 0, derivative of negative 16t squared is negative 32t. All right, so I'm going to find then v of 3, which is negative 32 times 3, which is negative 96 meters per second. And that is actually the velocity at impact. Okay? All right, that's the velocity at impact. So let's go ahead and take a look at another problem. Okay, so here is our next example. This one right here is kind of a business example. Business uses a lot of calculus. Economics uses a lot of calculus. This could also be considered kind of a economics problem, if you will. If you're taking economics, they talk about things like marginal cost, marginal revenue. So what does it mean? Well, this marginal cost in this case is the rate of change at which we're producing some good. The cost anyway, the rate of change of the cost of which we're producing some good. And so here we want to figure out, well, at this current production rate, what is the rate of change of the cost? You know, because at some point, you know, maybe the more that you produce, the cost goes down. Okay, so that's kind of what's going on here. So let's take a look at this problem, and they tell us that the cost function is represented or modeled by this function c of x, which equals 400 plus 20x minus 0.2 x squared. To find the marginal cost, we're asked to find the derivative c prime of x. This is the cost function. This one is the marginal cost function. Okay, it's the derivative. So we get 20 minus 0.4x. Okay, 20 minus 0.4x. And then what we do is we want to find, well, what is the marginal cost? What is the rate of change of cost when we produce 35 radios? So that's c prime of 35. So we're going to plug that in here. 20 minus 0.4 times 35. And what do we get? Okay, we get 20 minus 14, which is 6. So $6. So that's the marginal cost. The cost of producing these radios is $6 when we've produced 35 radios. So marginal cost could go up, could go down when we've produced the 36th radio. All right. And actually, I think it's pretty clear that if you produce another radio, the cost will actually go down. Or in this case that you produce, the cost per radio goes down. All right. So really nice example, but let's go ahead and take a look at another problem. Here we've got this kind of circular oil spill. So let me see if I can draw a picture. Here's my circular oil spill. All right. And what's going on here is that the oil, it's expanding in a circular pattern. All right. And the question says, at what rate does the area change? So we know obviously that this is going outward, so the area is going to be changing. Okay. The area is going to be changing. At what rate does the area change with respect to the radius when r equals 6 feet? So again, another calculus problem. We've got a equals pi r squared. Our variable here is r. Our rate of change that we're looking for is a prime. Okay, so pi is a constant, so r is like your x. So if it was x squared, derivative would be 2x. In this case, r squared, the derivative is 2r. We multiply it by pi. So 2 pi r in this case. And we know that the radius here was given is 6 feet. Okay, 6 feet. So a prime equals 2 times pi times 6, which is 12 pi. Okay, 12 pi. All right, so 12 pi feet squared per foot of radius. All right, so 12 pi feet squared per foot of radius doesn't quite sound right because you're probably thinking, oh, feet squared per feet has to be 1 foot. But this is the rate of change of the area per foot of the radius. So two different quantities, area versus the length of the radius. Okay, so that's the rate at which that one is changing. All right, and I think we have time for just one more example. So let's go ahead and take a look at that. Okay, so let's pretend here that we've got this nice Olympic-sized swimming pool, and it says the number of gallons in the pool. All right. And let me draw some water just to give it a little more of a pool feel here. It says the number of gallons of water in a swimming pool t minutes after the pool has started to drain is Q of t equal 50 times 20 minus x quantity squared. How fast is the water running out at the end of 14 minutes? So they want the rate of change at the time 14. So basically they want us to find Q prime of 14. Well, in order to find Q prime of 14, we have to find Q prime of t. All right. Now, this one's an interesting problem because we actually don't have formal rules for evaluating a function that looks like this, kind of a composite kind of function. So what we're going to do first is we're going to do the algebra behind this. So we're going to do the binomial expansion. So we've got 50 times and then 20 minus x quantity squared is going to give me 400 minus 40x plus x squared. And then I'm going to distribute that 50 that was out in the front. So my Q of t will be something like, I think it's 20,000 minus, and then it's 2,000x plus 50x squared. Now I'm ready to find my Q prime of t. Okay, my Q prime of t. So I take the derivative. I'm going to get derivative of 20,000 is 0, so that doesn't matter there. But I have a negative 2,000 from the negative 2,000x plus 100x. Okay, when I take the derivative of that. And now I'm ready to find my Q prime of 14. All right, what does that look like? Negative 2,000 plus 100 times 14, which is negative 2,000, plus 1,400. So the water is coming out at a rate of 600 gallons per minute. So if you can imagine, the water is just going down the drain at a rate of 600 gallons per minute. That actually sounds kind of fast if you think about it. All right, so this right here, perhaps we don't need the sign negative, but let's say 600 gallons per minute, because the context of the problem says that how fast is the water running out? 600 gallons per minute. Okay, so you might not need the negative 600 or the negative sign if you're typing your answer into some kind of computer system or homework system. All right, but hopefully you've enjoyed these applications that we've gone over. I hope they were helpful, and as always, like and subscribe.